SwayamPrabha. Digital India. Educated India.
Welcome back. Now that we have been introduced to Laplace transform and derived Laplace transforms for some of the important functions, let us try to make use of those in solving diffusion equation. So, the solution for steady state conditions we have already seen. So, next few classes we will try to solve diffusion equation for non steady state condition. So, the diffusion equation that we are talking about is partial of C with respect to t equal to d second partial of C with respect to x. So, obviously, when we write this equation we are assuming that d is constant. Now, this equation is first order in time t and second order in distance x, which means we need one initial condition and two boundary conditions to solve these equations. So, we will see how we can solve this equation for different initial and boundary conditions. So, let us start with the solution for instantaneous planar source. This is an important boundary condition that is encountered in some of the applications. For example, in semiconductor industry, the doping of silicon is carried out by diffusion process, right. So, in there what they do, the silicon semiconductor is first deposited with the thin layer of dopant on the top surface. This is a very thin layer. This is the deposition step, and then this assembly is heated at an elevated temperature. So, that the dopant now starts diffusing into silicon. Now, it is very important to control the concentration at the desired depth. So, we need to know at a given time the given concentration plane has penetrated to what depth, or at a given distance what is the concentration of dopant, and for this we need the solution based on this diffusion equation. Okay. So, this is the instantaneous planar source. What is the initial condition here? So, to start with, there is no dopant in the silicon, or if we are considering the diffusion of let us say material B in A, initially A is pure. The initial concentration of B in A is 0. Right. So, and that is 0 everywhere except on the top surface, and the surface layer which is deposited is extremely small. So, for the purpose of solution we assume that this thickness is 0. So, for the purpose of solution we assume that thickness of the layer is 0. Right. So, our initial condition becomes concentration at any x at t equal to 0 is 0 for all x greater than 0. So, in this case our x equal to 0 is on the surface and the x is increasing with the depth, right, downwards. What are the boundary conditions? So, typically width is large compared to the distance to which B can diffuse in A at the given temperature and time, which means B will never diffuse all the way and reach the other surface, right. So, the other surface still remains pure at any time. So, mathematically we say that at x equal to infinity at any time t, the concentration is original concentration, which was 0, right. So, our x equal to infinity is the other surface. What is the second boundary condition? So, initially we deposited some quantity of material B. So, let us assume that the quantity that was deposited per unit area, let us say, is delta per unit cross sectional area, and after that we are not adding or removing any material, right. So, this delta amount per unit area, if we just follow the unit cross section, and this is a unidirectional diffusion, right. So, at any given time the total quantity, if we look through the entire thickness of A, it should remain constant equal to delta, right. So, if we integrate C dx from 0 to infinity, that should be equal to delta, right. So, we have question 1 based on the initial condition 2 and the boundary conditions 3 and 4. Now, we will make use of Laplace transform to solve this. To do that, if we multiply both sides of equation 1 with e to power minus k t and integrate within the limits of time equal to 0 to infinity. Integral 0 to infinity e to power minus k t dou c by dou t dt equal to, since d is constant, we can take it outside, integral 0 to infinity e to power minus k t dou 2 c by dou x 2 dt. Now, let us try to solve each side one by one. So, if you first look at the left hand side, LHS, which should be equal to integral 0 to infinity e to power minus k t dou c by dou t dt. Now, this integral we can solve by the method of integration by parts. So, if we integrate by parts, what is the formula for integration by parts? Integral a to b u dv is equal to u v within the limit a to b minus integral a to b v du. So, we have to select u and dv appropriately from this integral. So, if we write u equal to e to power minus k t and dv as dou c by dou t dt, and obviously my du is minus k e to power minus k t dt and v is dou c by dou t dt is dc. So, v is nothing but c. So, we substitute in the integration by part for u and v, or LHS becomes u is e to power minus k t times v is c from 0 to infinity minus integral 0 to infinity v du, v is c and du is minus k. So, okay, this is a constant, let us take that out, minus minus becomes plus e to power minus k t dt. So, if we take the values of e to power minus k t and c at t equal to infinity, e to power minus k t at infinity is 0 and c at any position x at any time has a finite value, right, that was the initial condition. So, this is 0 and at t equal to 0 e to power minus k t is 1 and c at t equal to 0, c at x 0. plus, now this integral looks familiar. What is this? Integral 0 to infinity e to power minus k t times c dt is the Laplace transform of function c, right. So, let us denote that by c bar. Now, we know the initial condition C at x at t equal to 0 is 0. So, LHS comes out to be straight k times c bar, where c bar is the Laplace transform of function c. Now, let us take the second side RHS. RHS in this case is d integral 0 to infinity e to power minus k t dou to c by dou x2 dt. Now, e to power minus k t is not a function of x. So, we can take it inside the partial differential here, that becomes d integral 0 to infinity dou 2 by dou x2 of e to power minus k t times c dt. And next we can change the order of integral and differentiation. So, this becomes dou 2 by dou x2 of integral 0 to infinity c times e to power minus k t dt. Again we encounter the integral for Laplace transform of c. So, this equal to d dou 2, this integral is nothing but the Laplace transform of c, which we denote as c bar. So, dou 2 c bar by dou x2. Now, we know this Laplace transform is the integral with respect to t, and this is a definite integral. So, this is independent of t, right. So, c bar is not a function of t now. So, we can replace this partial differential with ordinary differential. So, we can write RHS is equal to d times d2 c bar by dx2. And so, if we substitute for LHS and RHS, k c bar equal to d d2 c bar by dx2, or if we rearrange d2 c bar by dx2 minus, if we take d on this side, k by d c bar equal to 0. This is interesting, right. So, we had a partial differential equation in x and t, and Laplace transform has helped us to transform it to an ordinary differential equation in x, right. Now, we know the general solution for this equation. So, let us take c bar equal to e to power lambda x as the solution. So, if we substitute here, so d c bar by dx is lambda e to power lambda x, and d2 c bar by dx2 is lambda square e to power lambda x. So, we can write lambda square e to power lambda x minus k by d e to power lambda x equal to 0. So, this gives the value of lambda as plus or minus square root of k by d. So, we have two solutions here. One is c bar equal to e exponential minus root k by dx exponential plus root k by dx, and we know the linear combination of solutions is also a solution. So, we can write the solution as c bar equal to p, some constant p, times exponential minus root k by dx plus q exponential plus root k by dx. Now, we need to find out the values of these constants p and q. We can determine one of them straight away based on looking at our boundary conditions. Now, what happens here if x is infinity? The first term will be 0, as x tends to infinity, the first term will tend to 0, but the second term will tend to infinity, right. So, but we want even at x equal to infinity, we should have a well behaved solution for concentration, right. So, if we need to get any physically meaningful solution, that q has to be 0, right. So, q is 0 here. So, we are left with only the first term p exponential minus root k by d x. And to find the value of p, we now use our second boundary condition. What was that? Integral 0 to infinity c dx is equal to delta. Again we take Laplace transform on both sides. So, we 0 to infinity integral 0 to infinity e to power minus k t into c first dx and then dt is equal to delta is a constant. So, we can take it outside of integral. So, 0 to infinity e to power minus k t dt. And if we change the order of integration on the left hand side, we have integral 0 to infinity integral 0 to infinity e to power minus k t times c dt dx is equal to integral e to power minus k t is minus 1 by k e to power minus k t. So, minus delta by k. Now, e to power minus k t at infinity will be 0, e to power minus k t at 0 will be 1. So, this should be equal to delta by k. And again this is the Laplace transform, the inside integral is the Laplace transform of c. So, integral 0 to infinity c bar dx should be equal to delta by k. Now, we know the equation for c bar. So, we substitute for c bar from here. So, integral 0 to infinity p is a constant, let us take it outside, exponential minus root k by d x dx is equal to delta by k, and integral of exponential minus root k by d will be minus root d by k exponential minus root k by dx. So, this should be minus p times root d by k, and exponential at minus infinity is 0, exponential at 0 is 1, and so we get the value of p as delta by root k d. So, the solution becomes c bar is equal to delta by root k d exponential minus root k by dx minus root k by dx, right. So, we found the solution for c bar, and c bar is a Laplace transform of c. To get back to c, we need to take inverse Laplace, right. So, c of x and t will be L inverse of delta over root k d exponential minus root k by dx. Now, we have studied before L inverse of 1 by root k exponential minus a root k should be equal to 1 by root pi t exponential minus a square by 4 t, where a is a constant. We can compare our solution for C bar with this function on left side here, right. So, if we do that, it is on C bar, in the solution of C bar, delta by d is a constant, right. So, 1 by root k exponential minus root k by dx. So, if we compare with this function here, the value of a here is x by root d, right. So, we have a is equal to x by root d, and so we get the solution for C as delta by root d is a constant. So, that will appear delta by root pi dt exponential minus a square by 4 t, a is x by root d. So, it will be minus x square by 4 dt, and so this is the solution for diffusion equation for instantaneous planar source condition. So, this is an important solution. As I said, it is very important during the doping of semiconductors, right. That is where we need to refer to this solution. The process of diffusing this dopant into the silicon chip or any other semiconductor is called drive in, and if we need to know how much the given concentration plane has penetrated at a given time, we need to refer to this solution. Now, here we assumed d is constant, and this assumption is very close to reality in such cases. For example, the dopant concentration is typically very small, right, in ppm. So, at that small concentration we can assume d is constant. Okay. So, that is one use of this, right. Where is another use? So, another example of where the application of this particular equation is in the field of diffusion itself. You guys have heard of tracer diffusion experiments? Right. So, this equation is also used for measuring the diffusion coefficients, particularly the impurity diffusion coefficient of, let us say, B in A. How is it done? Let us see first mathematically, then I will explain the experimentally. If we take logarithm on both sides of this equation for C of x t, we will get ln C equal to ln of A times B is ln A plus ln B, and ln of exponential. So, this becomes minus x square by 4 dt plus ln of delta over root pi dt. So, this is a simpler form which tells me if I plot ln C against x square, what should be the nature of the plot? Should be a straight line, right, with the slope. What should be the slope? Minus 1 by 4 dt. So, this gives me idea of how I can measure this term diffusivity term D, let us say for impurity diffusion of B in A. Right. So, if we can have a similar assembly as described before, if we want to measure B in A, I take the substrate of A and deposit a very thin layer of B on the surface, and this assembly is heated so that B is allowed to diffuse into A isothermally. This is done at constant temperature, right, for some time t. Then after the diffusion experiment stops, I can plot the concentration as a function of x. I can measure concentration as a function of x, and then if I plot ln c versus x square, I should get the straight line. Again, this is an impurity coefficient. That means, the impurity coefficient of B in pure A means that it is the diffusion coefficient for extremely dilute solution of B in A. Okay. So, again the concentrations that we are dealing with here are very small, and we can assume D as a constant within the small concentration range that is encountered here, which is close to reality. Now, experimentally there is a little challenge, although this looks very simple mathematically, but measuring concentration at that small scale of values is not possible, right, with the typical concentration measurement setups that we have, like WDS or EDS. So, what they do, we cannot directly measure this concentration, and to measure the concentration gradient we need to measure them with pretty much good accuracy. So, what they do, they use radioactive isotopes of B in this case. So, instead of depositing the normal B, they deposit radioactive isotope of B and they carry out this experiment. Then they measure the intensity of radiation on the surface, and the intensity of radiation is related to the concentration. And to get the profile of intensity versus depth, we can remove the layer by polishing, and every time we remove small layer, measure the intensity, again we remove the small layer on the surface, measure the intensity, and that is how we experimentally obtain these profiles. So, this is one important solution that we studied, which is very useful in many applications. Now, let us try to see how the profiles actually develop. So, if we try to plot C versus X based on the solution that we have seen, and this is our block of B. Originally this is x equal to 0, and we call the other end as x equal to infinity. Again, although this block is finite, the other end we call as x equal to infinity, because in the given time the diffusant has not penetrated all the way up to the other side. As long as that is true, this infinite boundary condition will be satisfied and this solution can be applied. But if we select the thickness for the given time such that the diffusant penetrates all the way up to the other end, then we cannot use that solution, right. So, in this case, if we draw the profiles at different times, So, let us say at some time t, we will see that it will be something like this. Some other time. So, this is at time t 1. As the time progresses, the diffusion spreads into the material, and obviously the concentration on the surface will keep dropping. This is how the C versus X plots will look like for this instantaneous planar source solution. Now, let us look at so, in this case, instead of the instantaneous planar source of B in A, what I am doing, I am sandwiching an instantaneous planar source of B in 2 infinite blocks of A. Infinite in the sense again that the diffusion does not penetrate to the other end during the diffusion time. Now, we are solving the same equation. But the boundary conditions will be little bit different, also the initial condition. So, initially we have C at any x at time t equal to 0 would be 0 at any x not equal to 0. So, this is x equal to 0, x equal to plus infinity and x equal to minus infinity. Boundary condition again, C at plus infinity at any time t is 0, and then the total amount of B, which is basically C dx, should be equal to delta, and the limit of integration here would be minus infinity to plus infinity. So, unlike the previous case, now the diffusant is diffusing in both the directions. Earlier it was on the surface, so it diffused in only in one direction. Now, here it is diffusing in both the directions. So, we can follow the Laplace transform procedure and we will get to the similar type of solution. C bar is equal to p exponential minus root k by dx plus q exponential plus root k by dx. Now, in the previous case we had only positive values of x, but here we have negative as well as positive, right. So, if we look at the solution and at the boundary condition, we will see that when x has a negative value, the first term becomes infinity at x equal to minus infinity, right. So, for negative values of x, the first part should not be there. Similarly, for positive values of x, the second part should not be there, right. So, we can write C bar is actually p exponential minus root k by dx for all x greater than 0, and it is equal to q times exponential plus root k by dx for all x's less than 0. Now, we need to find these constants p and q. We will use our second boundary condition, which is integral minus infinity to plus infinity c dx should be equal to delta. If we look at our system, on both sides we have pure A and the diffusivity is constant, it is a unidirectional diffusion, which means the solution will be symmetric about x equal to 0, right. That means, at any given instant, out of the total amount delta of B, which is diffusing inside the two blocks of A, half of it will be on left and half of it would have diffused on the right, which means we can split this integral as integral 0 to infinity c dx should be equal to delta by 2. So, if we take Laplace transform again on both sides, delta by 2 is constant, and we rearrange, we will find the Laplace transform of C appears. So, that should be C bar dx is equal to delta by 2 e to power minus infinity is 0 and e to power of 0 is 1, and there will be a factor of minus 1 by k. So, this will be delta by 2k. And if we substitute integral 0 to infinity, which is positive value of x. So, we use the first part. So, integral 0 to infinity p exponential minus root k by dx minus root k by dx is equal to delta over 2k. So, this comes out to be minus p root d by k, exponential minus infinity is 0, exponential 0 is 1 is equal to delta by 2k, or p is equal to delta by 2 root kd. Now, with the similar treatment on the left hand side, we can show the q will also be same. Right. So, our C bar will be delta by 2 root d times 1 over root k into exponential minus root k by dx for 0 less than x less than infinity, and q exponential delta over 2 root d times 1 over root k exponential plus root k by dx for minus infinity less than x less than 0. So, again we can compare with the Laplace transform that we know. So, C will be L inverse of delta by 2 root d into 1 by root k exponential minus root k by dx for x greater than 0 and equal to L inverse of delta by 2 root d 1 by root k exponential plus root k by dx for x less than 0. So, if we compare with our formula that we saw earlier, we will see in the first case for x greater than 0, a is equal to x by root d, whereas in the second case a is equal to minus x by root d. But it should not matter, because inside the exponential a appears as a square, right. So, for both the cases we have the solution C equal to d delta by 2 root d is a constant. So, delta by 2 root pi dt exponential minus x square by 4 dt. So, this is the solution when we have an planar infinitesimally small in thickness planar source sandwiched between two blocks of A. If we plot this, so on my y axis is concentration, x axis is x, this is x equal to 0 minus infinity plus infinity. Obviously, the solution is symmetric because d is constant. So, we will see get something like this. This is a T1, this is a T2. So, this is a typical Gaussian type of solution. T1 less than T2 less than T3. With time, we can see the peak of the profile is decreasing, and the peak is at x equal to 0, and the width of the profile is increasing. That means, the penetration depth is increasing with time, but the peak is decreasing. So, diffusant is spreading into the material. This is obvious because the total amount delta is constant. As it is spreading inside, the peak value has to decrease. Right. How do you find the peak value here? It is at x equal to 0, right. So, if we substitute x equal to 0 in this equation, so if I C naught is equal to delta by 2 root pi dt. So, we are seeing it is as 1 by root t. So, it should decrease with time. Also, if we try to find the distance at which diffusant concentration has dropped to 1 by E times the peak value. So, C by C naught is equal to e to power minus 1, and from this equation that should be exponential minus x square by 4 dt, e to power minus x square by 4 dt. So, what we get, let us call this x e. X e is equal to 2 root dt. So, if we follow this plane at which concentration is 1 by E times the maximum concentration, that is moving as a function of square root of time. That means, the diffusant is spreading inside, at the same time the maximum concentration is decreasing. Clear? So, we will stop here for today. Next class we will go over solutions for other boundary conditions. Thank you.